In one week earlier in the year, I found myself teaching essentially the same thing in 3 different lessons. We were looking at colour depth, so how many colours you can represent in a given number of bits. We were looking at truth tables and thinking about how many rows in the truth table you'd need for a given number of inputs. And then we were also talking about, the processor, the fetch execute cycle, and the bus and the memory address register. So we're thinking about how many different addresses you could address with a certain number of bits size, and the difference between a 32-bit computer and a 64-bit computer. So that's when I thought, well, actually it'd be useful to highlight to students how all these things are linked, so that when they come to revise, effectively they're only revising one thing instead of those 3 separate things. So the presentation that I'm about to show you is available for download from the website, including from this page, which is where all the items on the website are linked to the J277 OCR specification. So in the bottom, at the bottom, there's this themes section. So we're going to have a look at the combinations one now, and the next video is going to be the true and false one. So I try also to link in with other subjects. So as a teacher of some maths, I also know what students do for their GCSE in that subject. So if you can link it to that as well, and they can see the common themes, then that would help them even further. So I started off by saying, well, if you toss one coin, how many possible outcomes are there? So there's 2 sides to the coin, and most students are okay with this, and you've probably in maths seen something like this. So we talk about actually the more times you do something, the more representative the result is. So if you toss 10 coins, then you might get 8 tails and 2 heads, although you'd expect about 5 of each. But that's a maths idea. So students will have done that sort of thing. And what they'll also have done is this sort of thing that what do we do if there's more items? How can we work out the number of possible combinations? So they'll have either written them out. So if we toss 2 coins, what do you get? You can have 2 heads, a head and a tail and a head, or a tail and a tail. Sometimes, to begin with, students don't appreciate that a tail and a head is different from a head and a tail. The order is important. And obviously, if we're talking about things like colour depth, there will be 2 different colours, 1 0 and 0 1. So you can make that link to binary. What about if we had a 3rd coin? Well, one of the things that students do in maths as well is they look at combinations of other ways, either describe how many combinations there are or write them out. So we also link into this kind of example. So imagine you've got your meal deal at your station kiosk. So there's 3 types of sandwich: cheese, egg and ham, and 2 drinks, water and orange juice. So how many possible meals could you have with that? So you could write out as a list of combinations like the coins. So you could say cheese and water, cheese and orange juice, egg and water, egg and orange juice, ham and water, ham and orange juice. So you might be able to see that there's 6. But actually, one of the other things they do in maths is this idea of a sample space. So you can represent this as a kind of table, and that links nicely into computing because effectively you can link that to a 2D array, and you can say what happens if we go horizontally across the table and what happens if we go vertically across the table. So cheese, egg and ham. So just write that on my whiteboard here. So you could write that as a table like this. So you could go cheese, egg and ham, and then you've got orange juice and water, and you could create that table, and that'll give you already combinations. So that box there in my table would be a combination of cheese and orange juice. And what you can see, if you think of this as a table and think of this as one of those kind of 2D array questions you might get in a GCSE, what happens if you go that way? So if you vary the row in the table, what you get is all the different things you can have with your orange juice. And if you go that way, if you vary the row in the table, then what you can get is all the different things you could have with your cheese sandwich. So ideas of combinations also come up in programming as well, and we'll return to that at the end. And then you could say things like, well, how many meal combinations are there? What if we had a choice of crisps? So that's another extra dimension. And what students also realise, because probably a more common maths question would be, how many outcomes are there if you roll a dice and toss a coin. So you'd have heads and tails and then the 6 outcomes on the dice. And what you'd do there is basically you'd multiply them together. So you've got your 6 choices for your dice and your 2 choices for your coin. And what you do is you multiply them together. So you get 12 combinations. So for my meal deal, what you've got is you've got 3 choices of sandwich, 2 choices of drink, and then 2 choices of crisps. So it's going to be 3 times 2 times 2, which is, so 3 times 2, which is 6, and then times another 2 is, so there's 12 combinations there as well. So 12 possible meal deals, and students should be okay with that because that's probably foundation GCSE for maths. So how do we work it out in general? We multiply the things together. So how does that relate to computer science? Well, binary values are those choices, aren't they? It's like having your 2 choices of drink or your 2 choices of flavoured crisp. So those noughts and ones are basically the same as salt and vinegar or cheese and onion or orange juice and water. So you've got 0 and 1, or sometimes you can represent them in different ways. So you can have true and false if you're talking about logic, or on and off if you're talking about hardware. Also, you can link it to storage media. So magnetic media. How does magnetic media distinguish between the 2 different values, 0s and 1s? So you can magnetize things in different directions, north and south, for example, or if you had barcodes, you could have black and white representing those things, or you could have things that reflect or don't reflect, so you could link it to optical media as well. And so if we're only using binary values, what impact does that have on the calculation? Well, actually, that makes it easier, doesn't it? Because we're only multiplying 2s. So if you've got 2 bits, 2 times 2. If you've got 3 bits, 2 times 2 times 2. And students will also be familiar with the idea from maths, even on foundation level, that they can use indices or powers to represent multiplying the same number by itself kind of multiple times. So if we had 3 coins, 2 times 2 times 2, we can also write that as 2 cubed. And you can again link that to your binary column headings as powers of 2 if you wanted to. So there's 4 light switches, for example. How many different combinations are there? It's 2 to the power 4. So it's 2 to the power of however many things there are. And obviously we can calculate those, evaluate, so that's a bit of terminology you could throw in there. 2 cubed, 4 cubed give 8 and 16. So that's the kind of basic calculation, the basic idea behind the maths of it. But where does that appear? Well, the common idea, or the common thing that they need to appreciate, is basically, with a given number of bits, how many different values can they represent? And because a collection of bits, 4 bits, is just a combination of 4 binary values, isn't it? So 2 times 2 times 2, so that's 16 different things. So it's exactly the same working out coins as working out bits and the number of values. So the number of values that can be stored using n bits is 2 to the power n. The thing that slightly confuses students is obviously in the same way that when we do, for n in range 10 in Python, that gives us 10 values, but they're not numbered up to 10, they're numbered 0 to 9. So the biggest value in 4 bits isn't 16, it's 15, isn't it? It's 1 less than that. And again, you can think of that in terms of, you can make the link with things like combination locks. So if they've got a 3-digit lock on their bike, for example, that's 1,000 combinations, but they're numbered 0 to 999. So you could think of them as numbers rather than combinations. So that might help as well. So the largest value you can store is 1 less than the biggest value, because we start counting at 0. 1 less than the number of values. So this links to things on the GCSE specification, such as colour depth. So the colour is stored as a number, so you can revise at this stage how representation works. Everything needs to be represented as a number, but what does that number actually mean? So the number of bits used to store each pixel is called the colour depth. How many different colours could you store if the bit depth was 2? Or basically, it's how many different outcomes are there if you toss 4 coins? Exactly the same thing. So 2 to the power 4 is 16, so 2 to the power of however many bits there are. What would that look like? Well, that's an interesting thing, isn't it? Sometimes students don't appreciate what that actually means and why that was so limiting. GCSE, they tend to use very small numbers, don't they? Because presumably because you've got no access to a calculator. So 4-bit colour isn't particularly realistic. So I did make a page to represent this. So what you can do is you can use the slider to adjust the number of bits that you use to represent a number, and you can see at the bottom the impact that would have on colour depth. So at the moment we've just got 1 bit which can be on or off, so that gives you 2 colours. They're not always represented using these exact colours, but typically it would be black and white for a 2-bit thing. Then we've got sound sampling, so the black line is the sound wave and the red bar is the value of the sample. So if you've only got 2 possible samples, basically it's going to be at the top or at the bottom, so that's not at all a good representation of that sound wave. And then on the right we've got what the truth table would look like if you had that many inputs. So if you've only got 1 input to your logic circuit, the only rows you're going to need in your truth table are those representing 0 and 1, and you can increase it. So what about if we have 2 bits? Well, 2 bits is going to be 4 colours. You can see straight away that's quite a big improvement in the sound, and we can see what the truth table would look like. 3. So you've got 8 different colours there. These colours, it just tell you at the bottom where they came from. So some of the lower numbers are from the BBC Model B in the 1980s, and when we get a bit higher there from things like CGA and EGA PC video cards from the 90s. And you don't have to get that high actually. So even that, 5 bits, certainly a lot more colours. If you think about what those colours would be used for, lots of logos and things, that'd be fine. Wouldn't be so good for a photo. Things about, if you think about how many different shades of green you might have in your grass, or how many shades of blue you might have in your sky. But once you get up to kind of 7, 8 bits, that's looking like a proper kind of palette, isn't it? Obviously, your truth table's getting a bit big at that point. So you can have a look at all these pages that I'm showing you, by the way. They're all on my website, all free to access. So you can have a look through the different sections. So this particular one is in the math section. The menus are getting too big now, so that's actually in the more section of the maths part of the website. So that's colour depth. So if you had a colour depth of 8, that's 256 colours. So that's an important thing to appreciate, that actually we've doubled the number of bits, we're not doubling the number of colours. So you can make another analogy there, or another link, saying, well, if you add an extra digit to your byte clock, if you had a 3-digit byte clock, that's 1,000 combinations. If you had an extra digit, that's 10 times as many combinations, isn't it? So each time we add an extra bit, we're doubling the number of colours. So 8 bits isn't twice as many colours. It's a lot more, isn't it? It's 16 times as many colours, in fact. And obviously that would look a lot better as well. So that's colour depth. Sound, pretty much the same. The number, the impact of the size of the number looks different because it's the number of different heights you can have on your sample. So again, if we had 3 bits, that's 8 possible values. That's not looking too bad. So it's 8 possible heights of red bar there. We're trying to represent the sound wave. It's a reasonable kind of facsimile. But if we double it to 6, that's 64 possible values. So again, not twice as many values, but 8 times as many values. 8 times as many because it's 3 more, isn't it? 2 to the power 3 is 8. So that's and that's a much better fit, isn't it, if you look at the diagram on the right. So again, I've made a page to represent that. It probably looks a little bit better if you have a look at that. So that's this one here. So at the bottom, just need to zoom out slightly. Got some sliders. And what you can do is you can adjust the sampling size and adjust the frequency. But I think the interesting one is the sample size. So it starts off at 8 bits. So you can see there's 256. And you can reduce the number of bits, so the number of possible heights for the bar. It doesn't work so well with a sine wave, but obviously that's easier to program. And you can see you can reduce the bit size, the bit bit depth quite a lot before you notice much difference. And that's basically how lossy compression works, isn't it? So you can demonstrate the link to that topic as well by showing students the sort of things you can discard without there being an appreciable difference. So effectively, if we reduce this down to 4 bits, it doesn't look massively different, but that's half as much data, isn't it? Obviously, if you go a lot lower than that, we can start to see the impact of reducing the bit depth there. Okay, so that's how it links to the representation topic. Also, we can link it to networking. So IP addresses, why do we need to move from IP version 4 to version 6? Well, IP version 4, so occasionally there's questions about this, I think, on the GCSE, had 4 8-bit numbers, basically. So the number of combinations there would be 256 times 256 times 256, which is 4.3-ish billion. And you might be thinking, well, that's quite a lot. That's about half the population of the world. But if you think about the devices that you have, you'll have multiple devices and multiple locations that you use those. So your first thought might be, well, maybe only half the population's got a computer. Children mightn't necessarily have one, people in remote locations, etc. But actually, we might need multiple IP addresses each. So we switched to IP version 6, which is 8 16-bit numbers. So if you work that out, we've got 2 to the power 16 is 65,536. So that's each of the 8 16-bit numbers has 65,000 different values. And then there's 8 of those, so that's 65,536 to the power of 8. Which is 3 times 10 to the power 38, which is obviously plenty for the time being. And similarly with addressing memory, so if you're talking about memory address registers or bus width, that's the same idea. There's a word, word. So we talk about word length, or we used to talk about word length more than we do now, I think. But that's basically the number of bits that your computer can deal with in one go. So you might talk about a 32-bit computer or a 64-bit computer. We're talking about word length there. That's the maximum number of bits that the computer can handle in one kind of transfer or one fetch. And obviously we talk about 8-bit computers back in the 80s, so the biggest number they could deal with in one go was 255. You might be thinking, well, 32 is plenty until, I don't know, probably 10 years ago, there probably were 32-bit computers around. I think some Chromebooks and possibly some low-end phones are still 32 bits. But 32 bits is 4.3 billion different values. And you might be thinking, well, that's quite a lot, isn't it? The biggest number you can store and handle in one go is 4.3 billion. I read a bit of research a few years ago saying actually something like 95% of the numbers we ever see in life are less than 20. So that's, unless you're an astrophysicist or something, then you're not going to deal with numbers of that size generally, and banking or whatever. But if you think about your memory address register, that means you can address 4.3 billion addresses, which is 4.3 gigabytes, which is probably less than most people have in their PCs now. So if you've got 8 gigabytes of RAM in your PC and you're running 32-bit Windows, you're not actually going to be able to use all of it. So that's the real benefit in having a 64-bit computer, is you've got a bigger memory address register and you can address more of your RAM. So if you've got a 64-bit computer, then your memory address register has 64 bits, which is 1.8 times 10 to the power 19 addresses. That's plenty enough RAM for most home users, I think. Similarly with truth tables, so not only has one input, that can be true or false, so you only need 2 rows, or 0 and 1 in this particular case. But if you go to 2 inputs, then you need to think about combinations, isn't it? That's again, it's like tossing you 2 coins. So you've got 4 possible outcomes. So if you think of 0 and 1 as heads and tails, it's exactly the same as that first slide. So so again, the number of rows you need in your truth table is 2 to the power of the number of inputs. So if you had 3 inputs, you'd need 8 rows, and that's again on that range of values website. I'll put a link to that in the description of the video. So again, you can also link this to security. So how does this link to that? Well, think about a password. That's a little bit more tricky to think of. So if you think of, again, combination locks to start with. So if you had a 3-digit, or if your friend had a 3-digit lock on their bike, how could you crack it? We used to do this, when I was a child in the 80s. We used to try and kind of open each other's bike locks. It wouldn't take you that long to try 1,000 different combinations. You could just keep turning them until it opened. If you had an extra digit, that would be 10,000, wouldn't it? So that would be quite a bit longer. If you had a 5-digit bike lock, that would be 100,000, take you longer still. So you could talk to students about, the complexity of adding extra digits to things like that, or if they've got combination lockers, for example, at school. So brute force is the way that we, basically just trying all those different combinations, isn't it? And it takes a little bit longer to twist the lock, and obviously, or try different key combinations with a physical product. But computers are very quick, so you can try different passwords, different numerical pins, for example, quite quickly using a computer. So you could talk about how you could prevent that. You could only allow 3 goes, or make sure that if you get it wrong, you have to wait before you try again, and so on. So brute force is both a security attack, but it can also be used to find solutions to problems. So there's lots of different links between different areas of the curriculum just from this one idea. And so I tend to show these presentations at the end of the year, or I have done this year. I will do in the future, just to kind of tie everything together and show students that actually about half the course is this, basically. It's interesting that just because there are different combinations doesn't mean they're evenly distributed. So if you're thinking about security, for example, there'll be an order in which it would make sense to try the combinations, because people aren't very good at picking combinations for their locks and their pins and things. And if you remember back to the early days of the lottery, typically they sold 30 million tickets, but there are only 15 million combinations, and it used to roll over all the time because people always chose low numbers, which for their birthdays and things. So that's that dark strip there. So the darker the dot, the more people choose that combination. So you can see it's darker in the low section. People use low numbers. People repeat digits. That gives you your diagonal line, etc. So you could talk about how a dictionary attack. So picking actual words, they're more likely as passwords. So that's the same idea as that, basically, isn't it? So password strength, what makes a good password? So students know that. Probably my son did that to death at primary school. So they know about increased length. Why does increased length work? Well, that's just more combinations, isn't it? And using a range of different types of character, well, that's just more values in each position. So that's just that multiplication idea. So why do different characters help? So if you think about it, if you only had letters, that'd be 26 values in each position, wouldn't it? But if you include upper and lower case, you're doubling it. So that's 52. And then if you add in the digits as well, that'd be 62. And then your additional characters, your special characters, would obviously increase that number. And why do longer passwords improve security? Well, because you're raising that number to a bigger value, aren't you? So you could do a demonstration with practical examples of that if you want to do. There's a website, How Secure Is My Password, which shows you how long it would take a typical computer to crack that particular password. This one's an interesting one. I got this idea for my maths class from a tweet, which was this. So imagine there's a number line that runs from 1,000 to 1 billion. And when I first saw this, I thought, why have they picked 1,000 rather than 1? And I think now, thinking of that bit idea, it's to do with the number of zeros, isn't it? So we've got 3 zeros and then 9 zeros. So what would you imagine was halfway between the two? So the question is, where would a million be on that number line? And it turns out that most people, I think it said about half of people, put it in the middle. So I actually made this into an interactive thing again on the website, which you can find. If you struggle to find any of these pages, just look in the index. So it starts off with a random position. So most people put it in the middle. And then you can see what that actually is by clicking on Show Value. So actually that is 491 million. And actually 1 million, well, depending on how big your screen is, you might not. So that's probably about as close as we can get with this particular resolution. So it's right down that end, isn't it? Because actually, a billion is a million times bigger. So and a million being so it's a thousandth of the way along that line, isn't it? So having done that with a maths class, I made you can add a query string. So if you say random equals and then a number, that number is the base. So it'll do it in binary. So if you say random equals 2, it'll do a binary version. So where is 32 on that number line? So 2 to the power 4, 2 to the power 6, you might think, well, 2 to the power 5 is in the middle. It's halfway between the two. But it's not. That's 41. So it's that idea, trying to break that misconception that the size of the number is directly proportional to the number of bits used to represent it. So then, so that's all places that I could think of that idea of combinations appear. Well, what about if you're generating them? So students will probably be familiar with the idea of straightforward loops by this point. There's a common question. You get something like this, where on a GCSE paper, occasionally it might be a program like this, and it might say how many times does the word hello get printed, or it might say how many times does row 3 get executed. And so students learn, possibly by rote, that you basically multiply these two things together. So when you run that program, you actually get 6 hellos, because lines 2 and 3 print it 3 times, and then line 1 does it twice. So 2 lots of 3 is 6. We can use those numbers if we wanted to. So if I said A and B, and we ran that, obviously we can get all the different combinations of numbers. What we can actually do, because 4 works with lists and strings as well, doesn't it? So you could do our sandwich thing, couldn't we? We could say, instead of having a range, we could use a list. So we could say egg, cheese, and what was it, ham? Doesn't really matter what it is. And then we could say, we could have another list here with the orange juice and water. So orange juice and water. And now when I run this, it's going to generate all the possible meals that we can have. Or if we do this with strings, we could say 0, 1, and we could say B, 0 and 1. So what this does, if you're not familiar with this use of for, basically it just makes the variable each thing in the iterable in turn, so each character in the string or each item in the list. And so if I put a plus in there instead, because they're strings, it's going to concatenate them. So what I get there is a binary counter. And most GCSE examples stop at 2 nested loops, don't they? But you can do this as well. So you can say for C in 0 and 1. And then obviously we can add in the third one as well. And then we've got ourselves a 3-bit binary counter. And it has all the properties of binary. It is actually counting from 0 to 7. And it's doing all the usual things. So the units column is alternating. The second column is alternating every 2. And so on. So I won't go through every slide in the remainder here. But it's some examples of how we can use nested loops to generate these combinations. So you can cover that as well. So that's the sandwich example. And this is the binary example. And you could swap that for coins, for H and T, if you wanted to do a probability experiment for maths or whatever. And so that's the end. But hopefully what you can see is that actually this one idea of combinations, we've looked at pretty much everything. We looked at storage, we've looked at representation, we've looked at programming, we've looked at Boolean logic, we've looked at security, and we've looked at networking, all with the same idea. So looking for opportunities to make connections across the curriculum and link things together is effectively reducing the number of things that students have to know, because just knowing that one idea of multiplying things together to generate the number of combinations is used in all those different topics.